Hi everyone, I'm going to show you in great detail how a Van de Graaff generator works, right down to the level of what the protons and electrons are doing. Those of you who already know all about electrons, protons, positive and negative charges, you can skip to around 1 minute and 35 seconds in. For everyone else, here's a quick introduction to those things. There are three things to keep in mind as I explain how Van de Graaff generators work. First, all matter is made up of atoms. I'll use the simplest model for an atom since it suits our needs just fine. In the middle of each atom are protons and neutrons, and spinning around them are electrons. The protons stay in the atom, but sometimes the electrons are free to move away. Second, the protons are positively charged and the electrons are negatively charged. The neutrons are not charged at all, so we'll ignore them. What does charge mean? Charge is simply a way of saying how the electrons and protons will behave. Things that have the same charge will repel each other, so two negatively charged electrons will repel each other, as will two positively charged protons. And things that have opposite charges will attract each other. So a negatively charged electron will attract a positively charged proton. And third, the objects made up of these charged particles can also be positively or negatively charged. If something has more electrons than protons, we say it's negatively charged. Notice that the protons are still there, just that there are extra electrons that aren't paired up with any protons. Alternatively, if something has more protons than electrons, we say it's positively charged. There are extra protons that aren't paired up with any electrons. And if we don't care whether a charged object is negatively charged or positively charged, we just say that it's charged. Here are the parts to a Van de Graaff generator. At the bottom of the back we have a motor here, which turns this roller. That roller turns this belt, which turns this other roller at the top. Also at the bottom we have this metal brush. In this particular Van de Graaff generator, that metal brush is connected to the metal case, and the metal case is connected to this ground wire, which is part of the power cord. So that ultimately goes to earth ground. That's not the case in all Van de Graaff generators though. In this small one right here, that bottom brush is connected to this metal dome right here. And in some Van de Graaff generators, the motor has a metal case and the brush is connected to the metal case. At the top is another brush, and in this Van de Graaff generator that's connected to this metal strip. I'll just put on the top dome, and you can see that that metal strip makes contact with the inside of the top dome. A Van de Graaff generator is a charge pump. It literally pumps charge from one end to the other. One end is a dome or partial sphere of some kind, usually on top. The other end can be a connection to earth ground, as with this one, or another dome, as in the small Van de Graaff generator I showed you, or the metal case of the motor. What's fascinating about Van de Graaff generators is that there are so many interesting things going on in them. Luckily, those things can be broken down into just a few steps. So let's start the explanation of how it works with the first of those steps. The purpose of this first step is to charge the bottom roller. When the motor's on, the roller turns, and that turns the belt. Depending on the materials, this causes the roller to become either negatively charged or positively charged. As the roller turns, the inner surface of the belt makes contact with the roller here and breaks contact here. If you have two different materials like these making and breaking contact, then they become charged. Electrons move from one to the other. This is called the triboelectric effect, and I have a video that goes into great detail about it. Because this roller is Teflon and this belt is rubber, due to the triboelectric effect, electrons on the belt will move to the roller. This means the roller will become negatively charged and the belt will become positively charged. We now have what we need for the next step, a charged roller, and in this case, one that's negatively charged. In this second step, we'll charge the outer surface of the belt. That's a charge that will be moving up to the dome on top. The roller, the belt, this bottom brush, and whatever the brush is connected to, in this case earth ground, work together to do this. Since this roller is negatively charged due to all the extra electrons, it'll be electrons that'll be repelled from the belt to the brush, leaving the outer surface of the belt positively charged. How will the electrons make their way to the brush? After all, they have to cross through the air, and air is not normally a good conductor of electricity. Well, the how is a little complicated, so let's take it one step at a time. The negative charge on the roller will repel some electrons from the sharp points of the brush. That leaves the sharp points on the brush positively charged. That creates a strong attraction between the abundant negatively charged electrons on the roller and the positively charged protons on the brush. Because there is this area between the electrons and protons where there is this attractive force, we say that there's an electric field between them. We can visualize the electric field by drawing a line from each extra electron on the roller to each extra proton on the brush. Since the ends of the brush are very sharp, the protons are tightly packed in there, and so the lines end up being close together. If we put an atom in the strong field, like this, then electrons from that atom may be pulled away from it, leaving the atom positively charged, what we call an ion. In fact, so much of this stripping off of electrons goes on that we end up with what's called a corona discharge, and if you turn out the light, you may be able to see it as a purplish glow. These positive ions are attracted by the negatively charged roller. On the way, they collide with other atoms and produce more ions. Eventually, some of these positive ions arrive in the area of the roller. But the belt is in the way of the roller, and so it's the electrons from the outer surface of the belt that get pulled to these positive ions. That leaves an area of the belt positively charged. The belt is then rotated by the roller, moving the positively charged area along on its way to the top of the Van de Graaff generator. The result is that electrons are transferred to earth ground, while the outer surface of the belt becomes positively charged. And that's the end of step 2. One more thing to mention before we go on to step 3. It was important that the ends of the brush be sharp points. Look at the electric field lines if a smooth surface was used instead. Each electron on the roller would repel an electron from the surface of the brush, and the remaining unpaired protons would be spread out more. The electric field lines would be less dense, which just means the electric field would be weaker. Electrons wouldn't be pulled from the air molecules, so no positive ions would be produced, and there would be no positive ions ending up at the belt to strip electrons from it. It wouldn't work very well at all. Recall that inside the dome at the top here, there's another roller interacting with the belt. In most home use or school lab Van de Graaff generators, this roller is either metal like this one, something that's triboelectrically different than the belt, or something that's neutral triboelectrically with respect to the belt. Before talking about my metal one, let's talk about the triboelectric ones. Remember that we charge the bottom roller by using the triboelectric effect. We can do the same thing with the top roller, but we want the opposite charge. To do that, we look at the triboelectric series table. This belt is rubber, which is in the middle of the table. The bottom roller is Teflon, which is at the negative end of the table, meaning it gets charged negatively. So we want something that's at the positive end of the table, as far away from rubber as we can afford so that it'll be charged a lot. As an example, many small Van de Graaff generators use glass by using the glass from a fuse or a small bulb. What would be the effect of using a glass roller on top? Due to the triboelectric effect, when it breaks contact here, the belt will take electrons from the roller, making the roller positively charged. What about the belt at that point? On the way up, and while it moves over the top of the roller, the inner surface of the belt is positively charged. With the addition of these electrons, now it either has the same number of electrons as protons, or has more and is negatively charged. What about a roller that's made of a material that's triboelectrically close in the table to the belt's material, rubber in this case? In that case, we can ignore the charging of the roller. And that brings us back to this particular roller, which is metal. As this positively charged belt moves up, it pulls electrons from the metal, not due to the triboelectric effect though. It does so because the metal is electrically conductive and gives up those electrons pretty freely as the positive charges on the belt attract them. That means that on the way back down, as with the triboelectrically charged top roller we just talked about, the inner surface of the belt either has the same number of electrons as protons or has more and is negatively charged. This is ideal because the bottom roller wants those electrons, so together the two rollers, with the help of the belt, reinforce each other's charging. Keep in mind that we've been talking about the roller's interaction with the inner surface of the belt. Up to this brush, the outer surface is still positive. We've talked a bit about the top roller and the belt. Now let's see how the top brush is involved. Step 4 is to use the now charged outer surface of the belt to move charge between the belt and the top brush. A similar thing to what happened at the bottom in step 2 will also happen here. We again have an air gap with non-conductive air that needs to be made conductive. Due to the charged belt, the sharp points on the brush, and possibly a built-up charge on the roller, there's a strong electric field, i.e. strong repulsive and attractive forces. This field either transfers electrons from the brush to the belt, or from the belt to the brush. With this Van de Graaff generator, the belt and roller are both positively charged, so this time electrons will be repelled from the brush and attracted to the belt. The strong electric field pulls electrons from the sharp ends of the brush and forces them onto uncharged atoms, turning the atoms into ions. But unlike in the bottom where our ions were missing an electron, these have an extra electron. Instead of positive ions, we have negative ions. We also still have collisions between ions and other atoms, resulting in more ions, some of them positive ions. But basically we again have a corona discharge. But unlike at the bottom of this Van de Graaff generator where the brush was positive, with a negative brush things are more complicated. After a collision has occurred, one of the atoms may lose energy by releasing a photon. This photon strikes an atom in the brush and causes it to release an electron. This is called the photoelectric effect. It's these additional released electrons that contribute a lot to the electrons that eventually reach the positively charged belt. Anyhow, once the ions arrive at the positively charged belt, the belt takes the extra electrons from the ions. This causes the atoms on the outer surface of the belt either to be no longer charged or to be negatively charged. And this means the half of the belt returning down to the bottom is either not charged or negatively charged. Anyway, that's how charge, in this case in the form of electrons, is moved from the brush to the belt. But where do the extra electrons come from? We'll find out in our final step, step 5. The final step is the charging of the outer surface of the top dome due to the Faraday ice pail effect. In this Van de Graaff generator, that charge will be a positive charge. The outer surface of the dome will have more protons than electrons. This makes sense since in step 4 we were moving electrons from the top brush to the belt. So the answer to step 4's question, where did the electrons come from, is the outer surface of the top dome. When an electron is attracted from the top brush to the belt, that leaves a missing electron in that position on the brush, meaning that area of the brush is now positively charged. This positively charged area attracts an electron from further along the brush, now leaving a missing electron further up the brush, and hence another positively charged area. This causes an electron further along the brush to be attracted to replace that one, and so on along the brush until we get to the dome. The next question though is why are electrons ultimately coming from the outer surface of the dome and not the inner surface? That's where the Faraday ice pail effect comes into play. One key to the answer lies in that the dome is all solidly electrically conductive metal, which allows electrons to flow anywhere attraction or repulsion causes them to. Another key is that as long as there is a repulsion or attraction somewhere, then electrons will move around the metal until there's no more repulsion or attraction, until all forces balance out. Let's do that again. We remove an electron, leaving another unpaired proton. But this time there's no unpaired electron around on the inner surface, so one will be attracted from the inside of the metal itself or from the outer surface. But that may leave a lone unpaired proton on the outer surface. That's okay, because there are plenty of unpaired electrons in the air, in the room outside the dome, in the walls of the room, or in the nearby trees if you're outdoors. The big difference between the inner surface and the outer surface is that the number of unpaired electrons and protons that can attract inside the dome is very limited and quickly runs out. This leaves the only way to interact with new ones by going through the metal dome. But for the unpaired electrons and protons on the outer surface, there's a whole wide world of other unpaired things to be attracted to. And so the outer surface will be charged and the inner surface will not be charged. But that all helps to understand another simpler explanation for why the outer surface is charged. Remember that like charges repel each other. Negative charges repel negative charges and positive charges repel positive charges. So when we pump electrons up to the dome, once they get there, they'll try to get as far away from each other as they can. And the farthest they can go is to the outside of the dome. But this Van de Graaff generator is pumping electrons away from the dome, leaving unpaired protons. The problem is protons can't leave the atom and wander around like some electrons can. So they may want to repel each other, but since they can't go very far, how do they spread out? The answer is they don't. As we pull electrons from the dome, the remaining electrons spread out. Notice that there are still more protons than electrons, but because the electrons spread out, that leaves the extra protons spread out too. There's still another question though. We built up this huge positive charge on the dome's outer surface. Meanwhile, we have this relatively small positive charge on the belt and brush that's trying to attract electrons away from the dome. Looks like we have an uneven tug of war. Wouldn't the positive charge on the dome win and the electrons not be attracted away? Well, since it works, the answer is obviously no. But why? Remember, we're taking these electrons through the inner surface of the dome, and the inner surface is not charged. So from the perspective of the belt and brush, they're attracting electrons from an uncharged object. If we had instead connected the brush directly to the outer surface of the dome, then the belt and brush would lose the tug of war, and the Van de Graaff generator wouldn't be able to build up a huge charge like it does. And lastly, since there's a whole world for the dome's charges to attract to, does that mean we can keep building up charge forever? Well, not quite. The outer surface is rounded, not sharp like the top and bottom brushes. But just like with the brushes, all those unpaired protons on the dome form an electric field with things in the surrounding room. If you keep pumping charge, eventually you'll pack so much charge that the electric field will become very strong, and once again we'll have corona discharge. In fact, if the other object is not very sharp, then electrons will pile up on one side until the air becomes conductive enough that it breaks down as an insulator altogether, and we get a sudden rush of electrons moving through it. That's why the rounder the dome, and bigger ones are less round than smaller ones, the weaker the electric field between it and surrounding objects, so the less corona we'll have, the higher voltage it can produce. And now you know in great detail how a Van de Graaff generator pumps charge from one end to the other, and also a bit about the triboelectric effect, corona discharge, the photoelectric effect, the Faraday ice pail, and more. Well, thanks for watching. Be sure to check out my YouTube channel, rimstar.org, for more related science and tech videos, especially in the Science and Tech playlist. Click to watch the triboelectric effect video, or my video on how to make a small Van de Graaff generator, one on exploring magnetic fields, and many, many more. I'd like to give a special thanks to 1011 Basic for doing some proofing on the second version of this video. Be sure to check out his channel. And be sure to subscribe if you like these videos, or give a thumbs up or leave comments or questions below. See you soon.